Yeah, well, good. We start. You may bring a chair there. Maybe you can shift. Good. Great seeing you. More people than I expected. People at different levels, with different levels of knowledge. So some of you already work in loop quantum gravity, some don't. These will be quite introductory lectures. So I hope not to lose those of you who know less. However, I hope they were going to be useful also for those of you who know a lot. I'm trying to give a sort of a slow elementary introduction to loop quantum gravity, but with all the main ideas. The way I view it now, after having worked on it for 20 years more. So what I'm going to do is to give general ideas, give the basic mathematics, give the basic formalism, try perhaps a few applications at the end. I don't know how far I will go. I want to go slowly. I want you to stop me, to ask questions, to tell me if you're not following. Let's try not to get lost and have no fear of saying this is not clear, whatever. There are a lot of books now on loop quantum gravity, many, by many people. I have two books. This is the 2004 Quantum Gravity. It has the main conceptual structure, has the main discussions about space and time and how to rethink mechanics, how to rethink quantum mechanics, all that, quite detailed. But it doesn't have the development of the last 10 years, which were quite crucial. And this is much more recent, and it's more introductory, and it has the theory as I understand it today, basically. There are other books by other people. I'm not going to list all of them. Refer to the books about the equations, not what I write on the blackboard, because notoriously I write plus instead of minus, 3 instead of 2, and things like that. So don't trust the details of the equations written on the blackboard. Most of them are in the books or in the papers, so refer to the book or the papers for precision. I have put a Dropbox. I've created a Dropbox with the PDF of the books, a couple of recent papers. I will probably add some to which I will refer, some even this morning, and a couple of the old basic papers, for the three main papers from which things developed. The Dropbox, I can send you an email with a link to the Dropbox, but if you go on my webpage, just Google Carlo Rovelli, you go on my webpage. In my webpage last night, I put a link at the beginning. There is a introductory quantum gravity course. There's a timetable and a link to the Dropbox. So it's easy access. You don't have to buy the book. If you buy the book, I get the royalties. I'm happy. All right, so that was for introduction. Let me start. So loop quantum gravity, that's what we're talking about. LQG. Now what it is a tentative theory for describing the quantum behavior of the gravitational field. It's tentative theory for quantum behavior of gravity, which, since we have learned from Einstein is also the quantum behavior of space-time, in a sense which is important to clarify, and I will clarify at the beginning. Why is tentative? Because we have no solid empirical support of it. So we start believing a theory to be a good description of the world after it has given verified predictions, new verified predictions. And for the moment we don't have any. My hope is to see verified prediction to be tested before before dying. This theory has been developed for more than 20 years, maybe 30 now. It comes in a number of variants with different formalism. Within canonical formalism, covariant formalism, within each formalism there are variants of the theory. So various people you talk to in the community, you get different perspective on it. The majority of things are in common. The community now is maybe 200 people, 300 people in the world, depending how you draw the perimeter of the community. There are sort of biannual conferences, maybe a dozen or more groups in the world that study loop quantum gravity, and the main applications so far are to early cosmology and to black holes. Here in Marseille we mostly recently have been focusing on black holes. For cosmology there is a very large community which is called loop quantum cosmology. Now the aim of the theory, this is important for avoiding confusion, is not to have the theory of everything. I don't believe we are any close to a theory of everything. We have no idea what's out there. We don't know what's dark matter. We don't know what happened at high energy. It's not to write the final arrival point of science or anything like that. It's just to describe the quantum behavior of gravity or the quantum behavior of space-time. Why? Because we have very well established theories that work spectacularly well, far better than it was expected when I was your age and was studying. We have 3 of them. Everybody's surprised by how well they work. They seem to describe everything, be able, at least in principle, to describe everything you can see, except a few things, dark matter being one. But clearly they don't describe the quantum behavior of gravity, which has direct implications because we don't know what happens in some actual areas of the universe. For instance, we now know the universe is full of black holes, many, millions. We know them by name, we observe them. We're building a huge telescope, the Event Horizon Telescope, which is a radio telescope by putting online many radio telescopes on the Earth, and we're going to very soon to have images of the black hole at the center of the galaxy, the Sagittarius A star, big black hole at the center of the galaxy, million suns. We see stuff falling in that black holes, and in other we see the accretion disk where we know that matter is rotating, spiraling and falling in. So we know that matter falls into the black holes. We know more or less what happened to matter because we have very good theories that tell us. So they cross the event horizon, go inside, we can theoretically follow what happens. What happened next, we have no idea. Okay, we really have no idea. So you take a stone, you throw it in a black hole, you can compute. We are told at school that we can compute what happened in physics in principle up to difficulty of calculations. Always, it's not true because you throw a black hole, it goes to the center, gets to the center, and then what? We don't know. We need a quantum theory of gravity because that gravity definitely is in a regime where we expect quantum effects, and we need a quantum theory of gravity. So a quantum theory of gravity purpose is to describe these corners of the universe where the present basic theories don't work. Now, before listing what we know about the universe, let me start by saying what we have learned recently about the universe. There is a false rumor that goes around that we have no empirical information whatsoever about quantum gravity. That's wrong. We have a lot of empirical information about quantum gravity, and we keep getting one. So, what is the empirical information we have? And I'll start from the recent one, and then I'll go back to the general one. So one crucial, it's a few months old, and is the discovery. It's a couple of years old, and is the actual measurement, detection of gravitational waves. And a few months ago, in fact, October 17, if I'm not wrong, there was the observation of this neutron star merging. Now, neutron star merging is a spectacular observation because it confirms a lot we know about the neutron star. It confirms general relativity in the strong field regimes. But the most interesting aspect of that observation, which is a few months ago, is that it was observed by the gravitational wave apparatus, LIGO, and not Virgo. Italian French as usually didn't see anything. But it also was observed by a lot of electromagnetic telescopes. In the optic, in the radio, in the high energy, it was observed by everybody. So there's big boom up there, and we observe that things. Now, the signal, the gravitational signal and the electromagnetic signal arrived together within a second from one another. A second could be an effect of the explosion. Now, this is a very far away thing, so it means that the gravitational and electromagnetic signal has traveled together at the same speed. Okay, so if you put the numbers in, the distance and so on, the neutron star merge, so 17, tell us that the speed of propagation of the gravitational waves divided by the speed of light is 1 with a precision in 1 part in 10 to the minus 15. That's what you find from the astronomers who have done this calculation. Now, before this observation, so 6 months ago, this ratio, which is of course a key, if you want, fundamental property of nature, was known in 1 part in 10 or 1 part in 100 from binary pulsars, from other things, because of course we had indirect observation of gravitational waves for long. So this means that with a single observation we have improved the knowledge of this ratio by 10 to the 14 by 14 orders of magnitudes. Okay, by what, a million, whatever it is, 1,000 billion, whatever, times. Okay. Now, why is this interesting? Because a lot of tentative theories of quantum gravity, other tentative theories of quantum gravity, are based on modifications of general relativity, where this ratio is very different. It's not 1. Okay, it's widely different. So, in one observation, we have almost ruled out, certainly put a lot of empirical pressure on a large area of research. Nature is saying, no, that doesn't seem to be the right direction. So we're learning things relevant to quantum gravity. The second observation, which is a few years old, I forgot the date, 3 or 4 years old, 4 or 5, which has taken everybody by surprise, by big surprise. In fact, I would say the majority of theoretical physicists have been shocked. It was not expected. Not all the theoretical physicists. Is supersymmetry observed at LHC. In fact, many theoretical physicists expected the supersymmetry to observed already at LEP before, but when LHC started a few months before, I remember going to Switzerland, to Geneva, and talking to them theoretical physicists there, and I remember them telling me, come on, Carlo, it's certain we're going to see supersymmetric particles. Well, it's not certain because we are scientists, we're open to big surprises, but come on. We have so many indirect arguments for low energy supersymmetry. There is string theory, there is dark matter, there is naturalness. It's completely different areas of our knowledge that point to the same thing, the existence of low energy supersymmetry. We're going to see them as soon as we turn LHC on. Now LHC has been on for years. No sign of supersymmetry. There are articles that you find online easily say no sign of supersymmetry on LHC. Now, why is this relevant? Again, it doesn't rule out directly any theory of quantum gravity, but it definitely puts stress on the direction of research that somehow was led to this prediction. Let me make a parenthesis here before going ahead. So a parenthesis about sort of philosophy of science and methodology. We all have learned about Popper, right? We all know something about Popper. And Popper told us that you don't really prove theories, you falsify theories. You don't really prove somebody right, but you can prove somebody wrong. So Popper sort of sketched this idea that science worked by proposing theories, testing them, to the extent in which nothing that they say contradicts reality, they might be okay, and then when they predict something which we don't see, the theory is wrong, we discard it. Now, this is super interesting. It's super interesting, especially as a demarcation criterion. So separating what is science from is not science. That was Popper's real aim. Was not to describe how science works, was to find a criterion to separate science from non-science. So astrology, make prediction, you test them, it's just false. It's just factually false. Or there are other things which could be extremely interesting by themselves. There's no negative judgment in them, but they don't give testable predictions, so they may be interesting, but they're not science. Science is testable prediction. But somehow people have taken Popper too seriously, saying that taking this as a description of how science works. That's not how science works. The way science works is that you have a theory, the more its predictions are verified, the more you believe it. The more predictions are not verified, the less you believe it, because you can arrange things. Right. So what actually happens is that you have a degree of confidence in the theory, which goes up and down. When general relativity came out in 1915, nobody believed it except Einstein and maybe Eddington. Then there was Eddington measurement, and so wow, maybe that's right. Then there was the calculations of the solar system in the 70s, and people wow, this is right. Then black holes were found. Then in the 30s there was the expansion of the universe, and then there was observation of gravitational waves. So now the theory is considered extraordinarily reliable in its domain. We know where its limits. There's an enormous amount of confidence because we have added the Maxwell equations, have had so many confirmations that in their domain of validity everybody believed them. Okay, nobody questioned the Maxwell equation in their domain of validity. To the point that if people write to me, I have proven the Maxwell equation wrong, I don't even read the thing. Maybe I should, because who knows? But no. And similarly, most theories are abandoned not because of a clear Popperian falsification test, Sometimes it happens. This was sort of one. But most of the time, you just abandon them because they're not fruitful. They don't go ahead. So this description of science in terms of fruitfulness, in terms of degree of confidence, which was more Bayesian, it's called today, close to Lakatos' description of science, even Kuhn in a sense. Why I'm saying all this? Why I'm making this blah blah blah? Because it's important for scientists, I think, enormously. You don't take seriously everything which is not being falsified. That's a mistake. And I think a lot of physicists today make this mistake. It has not been falsified, therefore it has to be taken seriously. No, bullshit. Okay, I have a theory that there are little green dragons the other side of the moon that hide very well every time we see them. Okay, can you falsify it? Maybe, but it hasn't been falsified yet. You take it seriously? No, it's bullshit. So it's not the absence of falsification that it's a good criterion for taking. So if you have a colleague that studies some strange Lagrangian, and you say, why are you doing that? And he says, why not? Can you prove it wrong? That's not a good scientist. Okay. We have never found anything about the world by randomly looking at things which have not been falsified. Right? We have found things new about the world by looking at experiments, by doing a contradiction within the theory, getting hints from nature, because we're not smart enough to get any theory. So no supersymmetry at LHC does not falsify supersymmetric theories. Maybe falsifies the minimal supersymmetric standard model. I don't. People tell me that. I'm not an expert on the. But there are other supersymmetric models that you can turn parameters. But the degree of confidence in that direction goes down. And goes substantially down. I mean, people are in trouble. People say, well, maybe I should study something else. That's the way science works. Third recent observation or set of observations is Lorentz violations. That has been a big story, a beautiful story, because there have been a number of attempts of writing a quantum theory of gravity which breaks Lorentz invariance. It's much easier. If you're allowed to break Lorentz invariance, it's much easier to write a consistent, mathematically consistent quantum theory of gravity. In fact, one example is Hojava-Lifshitz. Just write a Lagrangian, which is something that X and T are treated differently, and poof, you get a renormalizable Lagrangian. And since non-renormalizability was considered the main difficulty of Einstein theory, wow, it's so easy. So therefore, that's very good, because you have a prediction. So it's good science. I'm not saying that studying alternative theory of quantum gravity or studying supersymmetric theories or studying theories that break Lorentz invariance is bad science. It's good science. Immediately you have a prediction, namely that Lorentz invariance is broken. Where? At the Planck scale. At the scale where you expect quantum gravity effects. So people started writing possible violations, writing terms that violate Lorentz invariance and make prediction about them. And this was 10 years ago. And it prompted a sudden interest of people in astronomy to test this. And in fact, there was even a moment in which the first indication seemed to be positive. I got very excited. I wrote a research proposal because magic is one of these telescope things. We're detecting some light coming from some sudden burst far away, where the blue and the red were arriving at different time. So blue and the red, the high frequency, low frequency, they were separated by a delta t. Now, this is a clear violation of Lorentz invariance if the red and the blue, different frequencies go at different speed, because you have a different dispersion relation, right? It's like in a crystal. In a crystal, light doesn't go at the speed of light, because it interacts with the crystal, and the slowing with respect to the speed of light depend on the frequency. So frequencies go at different speed. So the idea is that, well, there's a Lorentz invariance breaking at the Planck scale. Planck scale is very small. So the speed of the different colors is slightly different, but if you look something very, very, very far away, you detect it on the lung. So magic kept telling that, keeping data, and it just disappeared. It experimentally disappeared. I'm not going into detail of how you test that. It's just not complicated, but a bit technical. But then there are a lot of other tests, and there's some globular cluster, the bullet cluster, in which there's some phenomena that depend, they're strongly characterized by the fact of being Lorentz invariant. And nowadays there are bounds on Lorentz invariance violation, which are very large, the order of 10 to the 6. So, if 10 to the minus 6. So, if the Lorentz invariance, the violation of Lorentz invariance at the Planck scale, they are very small. Or in other words, Lorentz invariance has been tested at the Planck scale with remarkable precision. Now, of course, it might be that there are other Lorentz invariance effects, not the ones that have been tested. So once again, we're not falsifying the idea that Lorentz invariance is violated, but nature is saying no. So come on, I mean that doesn't seem the direction to go. Nature seems to be, as far as we see, Lorentz invariant all the way to the Planck scale. And the theories that try to solve the problem of quantum gravity by breaking Lorentz invariance under enormous empirical stress. Okay. Once again, I mean, if you have a theory that there are giraffes in the Alps, it's not killed by the fact that you go hiking in the Alps and you don't see giraffe. Maybe they're just, in the forest, you didn't see them. But if many people goes in the Alps and nobody sees giraffes for very long, and if people studying giraffes say, well, they need heat, and it's cold in the Alps, and so on and so on, after a while you just forget studying a theory about giraffe in the Alps. So if you keep studying supersymmetric particles of low energy, Lorentz violation is like studying giraffe in the Alps. It's not Popperian falsified, but it's under enormous stress. Good. So these are recent results that tell us about nature. It doesn't seem that the kind of alternative to general relativity studied are experimentally favored. It doesn't seem supersymmetry, at least the low energy, experimentally favored, and it doesn't seem Lorentz violation to be experimentally favored. What do we know? So what are the positive things we know about the world? Well, as I said, what do we know about the world? We know three things, but we know them very well. And this is the three theories I mentioned at the beginning, that whose success everybody was surprised. And you know what they are. It's quantum theory, quantum mechanics, general relativity, and the standard model. Now, what is shocking about all three is that nobody took them very seriously at the beginning. When I was a student in Bologna, in Padova, and then started going around in London when I was young, nobody took the standard model seriously. Everybody was sure that it was going to be changed. The standard model was young at the time, it was basically just put together, and everybody expected it to be violated next week, next month. I remember when Carlo Rubbia he got the Nobel Prize, and he was going around saying that he had seen what was it, the the intermediate boson, vector bosons, that in fact confirmed the Weinberg-Salam part of the standard model. He was giving the talk, he was experimental, and saying, well, in fact, we're already having the data, we already see the violations with respect to standard model. So data not very clear yet, but next time I'm giving a talk, you will see what's wrong with the Weinberg-Salam theory. This was 30 years ago. I mean, it's 30 years that every talk from experimental I hear, well, it's just a standard model, we're already seeing some little violation, next time we'll be sure. 30 years, always the same. Okay? So the standard model is incredibly successful. So 30 years of everybody expecting it to be wrong, and everybody saying, well, actually we already have hints, next week we'll see. Yes?
Why do you not place thermodynamics in there amongst the pillars of science? Is it sort of subset?
Thermodynamics. Dynamics. I'm not sure it's spelled correctly. There is a sense in which it is even more fundamental than the rest. There is a sense in which it is not, because it is not a sort of list of basic stuff of the world and basic equations. It's something about the behavior of a lot of things under. We may spend time to discuss that. It's a little bit different status, people like Fermi and Landau, even Einstein, at some point said this is something we know much better than the rest, thermodynamics. So they are on your side. Other people would say, well, come on, this is just the behavior of many particles together, which is fundamental, but in another sense. Fundamental is a funny word, because it means at the basis, but at the basis with respect to which ordering. There are many possible ordering of things. It is relevant for quantum gravity, and I may say something quite ahead. Now, general relativity is even worse. I mean, general relativity, nobody believed black holes when I was a kid, right? I mean, I remember my general relativity class, the teacher saying, well, black holes is a solution of the Einstein equations, but kids don't believe there are actual black holes out there in the sky. Right. This was 75. Sinus, the first black hole, was actually already observed. People were still debating whether it's a black hole or not. Nowadays, nobody would say that. People would say, well, maybe a black hole on the long term behaves differently than what we expect, but nobody would say that these things are not well described by general relativity. And the observation of gravitational waves has been a test of general relativity in the strong field regime, which is a regime was the regime where GR was a little tested. So general relativity has been a spectacular success, far more than what people expected. And quantum mechanics, it's another of this story. I mean, you keep reading on the newspaper, wow, new experiment, fantastic result, incredible, has been done, blah 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 blah, starting from Aspet and now the Chinese with entanglement of particle, and the great result is that quantum mechanics is right. The equations written by Heisenberg in 1925 are right. Okay? So the great surprise is that the world is described by quantum mechanics. And there's people still surprised by that. It is described by general relativity, it is described by standard model. Of course, we don't expect that this is the end of the story, right? Because there's no quantum theory of gravity, and of course, general relativity certainly goes wrong. Sort of when h bar is different from 0, so small actions. Quantum mechanics most likely has to be readapted to take into account general relativity. Quantum mechanics, it depends on what you mean by quantum mechanics. If by quantum mechanics you mean the core of the theory, which we're going to go through, where no hints for saying wrong, it works very well. But if by quantum mechanics you mean the Schrödinger equation, the Schrödinger equation doesn't fit with GR because there is no t, there is no external time in GR. So the Schrödinger equation must be rewritten to quantum mechanics. So so must be sort of at the very least adapted to GR, which is what Dirac started to do, and it's a way we use quantum mechanics, sort of adapted to GR. The standard model, we don't know. It has been tested up to what, few TeV, 10 TeV. What happens at higher energy, sort of larger than 10 or 15 TeV? Nobody knows. Maybe there are other particles. Maybe there are other. Certainly, we have no idea what is dark matter. So, could be some other particle. Could be black holes. Could be. It's hard to think there is a modification of GR after that, but who knows? So this is what we this is what we know. And it is my understanding of the way that science works that if you want to understand the quantum behavior of gravity, we have to base it on what we know, and not base it on some fancy new idea pulled out of the sky, because fancy new ideas pulled out of the sky usually don't work. So the way loop quantum gravity works is to ask the question whether we can write a quantum theory that has generativity as its classical limit. So in other words, when we can write a quantum version of the theory such that in the h bar going to zero limit is generativity, and that's what loop quantum gravity is. Now, to do that, the key point is to, in my opinion, to take seriously the physics we know. The standard model is not much relevant to GR, to quantum gravity, because quantum gravity means quantum gravitational phenomenon, which are expected to be a much higher energy scale than this one. So it's not clear what it tells us, but quantum mechanics and generativity are the core. So loop quantum gravity is a way of doing quantum gravity, sort of taking generativity seriously, taking quantum mechanics seriously. That's what we know. Can we put them together? No fancy other stuff. No supersymmetry, no strings, no change of the theory, no. Can we just be theoretical physics? Take this, take that, bring together. That's the way Maxwell worked when he tried to put electricity and magnetism together. That's the way Newton worked when he tried to put Galileo physics and Kepler physics together. That's the way Einstein worked when he tried to put Newton physics and relativistic physics together, and so on and so forth. So, based on what we know. So, the starting point is what is this theory telling us? And I will spend time in that, and starting from generativity, and later on also about quantum mechanics. I think that a lot of energy in quantum gravity research is spent by trying to do theories which are not really relativistic or not really quantum mechanical. There are a lot of research out there which is called quantum gravity, which is not quantum theory, and a lot of research which is called quantum gravity, which is not general relativity. I am suspicious that this is going to work. Both these theories are strange with respect to our common intuition. Very strange. Quantum mechanics is unbelievably strange. Right? Entanglement is hard to digest once you put your hands in it experimentally. Generativity is even stranger in some sense. Tell us about things about space and time which are funny, very funny. So by bringing them together, I think this is quantum gravity. Merge and digest the strangeness of the two. And I'm going to start from there, from trying to clarify what generativity tells us, and then it will be a rapid build-up of the theory. So I close with one other sort of philosophy of science consideration to justify what I just said. There is another well-known philosopher of science, which is Kuhn, Where is the H in Kuhn? After the U or before the U? Before? After? Just like that? Or whatever, Kuhn. You know who I'm talking about. Kuhn also, it's very famous and it's very well known among physicists, and he told us great things about science. And he gave us this image of science which works, then has a crisis, and then in a crisis sort of everything goes wrong and you start from a different foundations. So you change the foundations. And it's a philosophy of science that sort of clarify the fact that science is a process. It's not just a big buildings that you build and you add pieces. It's a process in which you keep changing even the foundation. That's certainly correct. This historical vision of science is certainly the good one. We learn a lot from Kuhn. But like for Popper, it also had a bad influence on science. The bad influence is that if you take Kuhn, or at least the Vulgata, the version of Kuhn that is common among scientists, you get the impression that science is not cumulative. That every time you start from zero and you throw away all the rest. And we are taught that, right? Somehow Newton arrived, discarded everything as a new foundations. And then the 20th century arrived, Einstein discarded everything as a new foundation. Quantum mechanics discarded everything as a new foundation. And you have this image of science that what you knew before is irrelevant for what you build after. That's bullshit, okay? If you read Kuhn carefully, that's not what he says, but that's the way Kuhn is always. So you have this idea that in a great revolution you can discard everything, and once again you can, out of the blue, pull out new. If you look at the history of science is cumulative. We learn things which remain true, right? We learn that the Earth is round, and it's still round. Now, it's not exactly round. It's an orange. In fact, it's a pear, and it's a mountain, and we can learn. But it's mostly round. That's what we learn. It's not flat. It's round. We learn that the Earth goes around the sun, and it still goes around the sun. Now, general relativity is complicated because there is no absolute space, blah, 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 but it still goes around the sun. It's not the sun that goes around the Earth. It's a fact. We learned that there are electromagnetic fields, and that light is an electromagnetic field. It is an electromagnetic field. It's still true. We learned that there are black holes, that space-time is curved. It's curved. It remains curved, right? We keep learning. With the standard model, we've learned plenty of things. There are these particles. They are there. I mean, it's not. So we deepen our knowledge. We change foundation. We see things from different perspective, but we don't go back. We don't unlearn things. After Copernicus, those like Tycho Brahe who said, well, I can do better, so let's go back to the idea that the Earth is the center of the universe. This is dead directions of science. I believe that what we have learned about Lorentz invariance, okay, there's no preferred frame. It's a fact. Galilean invariance even. We're not going back to a preferred frame, like we're not going back to the Earth of the center of the universe. We'll not go back to a fixed space-time after general relativity. We'll not go back to a classical theory after quantum mechanics. We're going to learn more. Maybe the world is going to be more strange, more complicated, but we don't unlearn what we have done. So this idea that maybe what we have learned before is wrong, that's not science. Of course, it's hard to pinpoint exactly what is the key thing that will remain with us, but science is about adding knowledge and interpreting previous knowledge. It's not about discarding previous knowledge. So, loop quantum gravity is strongly based on this idea, because the source on which it's based is just quantum mechanics general relativity, and somehow it is in contrast with many other attempts to do quantum gravity, where you think, well, after general relativity we don't really believe what it says, or quantum mechanics we don't really believe what it says. So this is a general introduction about where we are, where is loop quantum gravity, and this was basically the first hour. So in the next hour I will start with a careful discussion of what we have learned about space and time in general relativity, and especially the discussion will be what we mean by space and time. Because in quantum gravity, space and time are going to necessarily mean something different than in general relativity. Like the electromagnetic field of the Maxwell equation is not the same thing as the electromagnetic field of QED. Right? In QED there are photons. Of course, there is we understand very well the relation between photons in Fock space and the electromagnetic field of Maxwell equations. We need to understand equally well the relation between quantum gravitational field and the gravitational field of Einstein of general relativity, which is space-time. So space-time has to be rethought quantum mechanically, but for doing that we need some clarity of what we mean by space, what we mean by time. So I will give in the next hour a discussion about space, what we mean by space, which is far from obvious and is, I think, needed to build a quantum theory of gravity. Time I'll deal later, because first I will talk about space, and after that we do some math and we start building the theory technically. So now we take a 10-15 minutes break, and then there's a discussion about space. Okay?